So hey, and welcome back to our lesson on proofs involving triangles. Before we get started doing any triangle proofs, you watched your video yesterday that talks about the 5 shortcuts to proving triangles are congruent. But I want to add some new definitions and theorems to your definition postulate and theorem sheet. So today you're going to be taking notes on your own, so plan on pausing the video, writing things down, drawing pictures, and even trying some of these proofs before you watch me go through and try them. So here's a case where in your definition, postulate, and theorem sheet, we already have all this stuff under angles, but here are the new ones that I want to talk about today. The first of the 3 is the definition of an angle bisector. And an angle bisector, you can read, ends up giving us 2 equal angles. And this is one of those two-way statements, that if you have an angle bisector, you get equal angles. But if you have equal angles and a line that goes through the interior of the angle, you can also say that that line must be an angle bisector. Down here is the definition of perpendicular lines, and that's lines that intersect to form right angles. And again, this is a two-way definition. If you have perpendicular lines, then you get right angles, but you can read it backwards. If you have right angles coming from 2 lines, then those 2 lines must be perpendicular. And finally, the last thing I want you to add to your definition, postulate, and theorem sheet is this theorem, that all right angles are congruent, or all right angles are equal. Now this is a one-way statement, meaning it only makes sense reading it from left to right. Obviously, if you have equal angles, they don't have to be right. But this is a one-way statement I would like you to add to your definition, postulate, and theorem sheet. Okay, so let's go ahead and let's get started with our triangle proofs. Do you remember from the video the other day that we have these 5 shortcuts, 5 very quick ways to prove triangles are congruent? Side, 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 angle, 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 side, and the last one is called hypotenuse leg. And of course, being called hypotenuse leg, you know it only works for right triangles. Now, the author of the video you watched the other day did talk about how angle side side doesn't work and showed you an example of how it doesn't guarantee that you could get 2 congruent triangles with that same angle side side relationship. So the placement of the angle in terms of the sides, very, very important. So here's our first proof. Why don't you take a second, pause the video, copy it down, and let's get started. Okay, welcome back. So when we get started on this proof, like most of our other proofs, I like to go in and mark my givens in the picture. So my first given, this red one, I know segment OR is congruent or equal to segment ER. So I'll mark those as being equal. And I know segment HR is congruent or equal to segment SR. And that's it. That's all I have for my givens. Now, if I'm trying to prove that these 2 triangles are congruent, I've got to have 3 things. You know, side, 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 those are 3 sides. Side, angle, side, 2 sides and an angle. Angle, side, angle. So every little shortcut for proving 2 triangles are congruent involves knowing 3 things. When we were given only 2 things, that means we've got some work to do. So that's why I look for freebies. And one of the quote-unquote freebies that I have in this picture is, look at these 2 angles, this one here and this one here. What type of angles are these? Well, they're vertical angles, and we know that vertical angles are always congruent. That's one of our angle theorems that we wrote down on our definition, postulate, and theorem sheet. So I think right now we have everything we need to prove these 2 triangles are congruent. We have 2 sides and we have an angle. And if you look at that placement of the angle, it's between those 2 sides. So this looks like we're going to be using an SAS strategy. So just like we did segment and angle proofs, I'd like to start out every proof by marking up my picture and kind of mapping out a strategy in my picture. Now let's write it up. So I know I need 2 sides and the angle in between. So my first step was my first given. And off to the side, I'm going to put this letter S. And what that letter S is telling me is it is one of the sides of these triangles. So I know up here, if I'm doing SAS, I already found one S right here in step 1. Step 2, I'm going to bring in my second given. That also is a side of the triangles. So again, I know if I'm trying to prove these triangles are congruent, I already have 2 sides. Third step, this is where we're going to name our vertical angles. Angle ORH is congruent to angle ERS. I can say that because vertical angles are equal. That's one of our theorems. And that gives me an A. And I like to keep track of my sides and angles off to the side. And once I have all 3, that tells me that I'm ready to go back in and I'm ready to name my congruent triangles. And so what I can say is triangle HOR is congruent to triangle SER. HOR is congruent to SER. And again, just like when we did similarity proofs, order is important. We need to match up corresponding parts. And the reason why these 2 triangles are congruent is by side angle side. Now, what's important is the placement of those sides and angles in the picture. See how the angles between the sides? Not the order in which we wrote it in, thank goodness, because we'd have something really bad here. It's the order that it appears in the picture. So let's take a look at another triangle proof and see how that works. It's a second proof dealing with triangles, and I tried to make my screen a little bit tighter for this one so we could see more things on the screen. So again, I have some givens, and I'm going to go in and I'm going to mark these givens on the picture. I know segment HM, that's this one right here, is congruent to segment HT, that's this one. And then I know that segment AH, this blue segment right here, this one going straight down, is perpendicular to segment MT. Now again, remember what we know about perpendicular lines. Perpendicular lines give us right angles. So I'm going to go ahead and mark that both of these angles here are right angles. So that's all the information that I was given. So what else do I have? What else can I use here? Well, I guess I have a pair of sides, and apparently I have a pair of angles, but nothing else. So I have a side and an angle. Oh, you know what? There's a freebie in this picture. Look, don't we know that this segment AH is the same segment for both triangles? So we could say AH is equal to itself, and it counts for both triangles. So what I see here is I see an angle sandwiched between 2 sides. Again, out of all of our triangle shortcuts, it looks like this is going to be an SAS, where the angle that we're talking about, the blue angle, is sandwiched between the red and the green sides. So let's write this thing up. Okay. Ooh, wait a minute. Look at this. I'm trying to prove triangle HAM is congruent, and I left this triangle blank. Let's see if we could figure out the order we'd have to write this second triangle in. Now remember, order matters. H, then A, then M. So HAM in the triangle on the left would go with HAT for the triangle on the right. So order matters. We've got to match up corresponding parts. So let's write this up. I always like to start with the given that requires the most amount of work. And I think that's the second given, because that doesn't give me a side and it doesn't give me an angle. It just tells me those 2 lines are perpendicular. But I can work with that. We know from our definition, postulate, and theorem sheet that we filled out just moments ago that perpendicular lines make right angles. So I can say these two angles, and again, notice how I use 3 letters to name those angles. I could say those are right angles, and the reason is it's the definition of perpendicular. Now, again, I'm not going to put an A off to the side. If I put an A off to the side, what I'm saying is that those angles are equal, and that's not what I've said. So I'm going to take this one step further and say angle AHM has to equal angle AHT. And the reason, if you follow the syllogism, statement 1 takes us to 2, statement 2 takes us to 3, and if we follow the syllogism, we would know that we just said they're right angles. And we have this theorem that says all right angles are congruent. Since these two angles are equal or congruent, and they're in both triangles, that's what gives us an A. So we've taken that given and we've run as far as we can with it. Now I bring in the second given, that these two red segments are equal. That's an S. Now I'm all out of givens, but remember this green segment, AH is equal to AH. AH is in both triangles, that's an S. And the reason, oops, I forgot the reason for number 4, it's given. The reason for number 5 is, that's the reflexive property. Any segment is equal to itself. You look in a mirror, you see yourself. That is a reflection or the reflexive property. Again, I have both sides and an angle. And if you look at the picture, the angle is between the sides. Look at the picture, not the way you wrote it up. And now we can end this proof by saying, whoops, I'm out of space here. I don't know why this is not moving. We can end this proof by saying triangle HAM is congruent to triangle HAT. And that is by SAS. Let's take a look at one more. This is the third and the very last of our proofs. And this time we're given that this MA is parallel to SH. So that lets me mark these two lines as being parallel. We're also told that they're equal or congruent to each other. So we know that they're parallel and we know that they're congruent. So let's see if we can prove that triangle MAT is congruent to triangle something. Now, let's see if we can fill in that something by acting out our proof in this picture. Well, what do parallel lines give us? Well, if you go back and you look at your definition sheet, way at the bottom, we know parallel lines give us equal angles. As a matter of fact, I can say that this angle, angle M, would have to equal angle H because they are alternate interior. Similarly, angle A would have to equal angle S because those are alternate interior angles. And since we have parallel lines, we know alternate interior angles have to be congruent. So I can tell right now that ASA, angle side angle, is going to be my strategy. And I know that because the side is between the two angles. This blue side is between these two gray angles. M in the top triangle matches H in the bottom triangle. A in the top triangle goes with S. And finally, T is vertical with T. So I think that's the name of my second triangle. So let's take a look at this proof. Again, I like to start out with the given that requires the most work, and I think that's the first given. Once we have parallel lines, we know that the natural syllogism is we should get some angles that are equal. So parallel lines here are going to take me to equal angles. M equals H, A equals S, and my reason straight from that definition sheet, if the lines are parallel, alternate interior angles are congruent. And that gives me two angles. Now, our third step, oh, I've lost it here. My third step is I'm going to bring in the next given, and that gives me a side. So I have two angles and a side. That's enough to say these triangles are congruent by ASA. You can start your homework. Have a good day.